Okay, we're back again, and it says know where the representative elements are located on the periodic table. I'm going to go down here and show you. It's the A group, so that's all of the S's and all of the P's. All of the S's and all of the P's. All right, so let's see if it'll let me write. All of the S block and all of the P block are the representative elements. Okay, so if you notice I didn't include these, the pink ones or the green ones. That's because these are transition metals. They can do all kinds of stuff depending on who they are attached to. So those are not representative. Okay? Just the S block and the P block. Know where various families and the S, P, D, and F blocks are located on the table. So you're going to have to tell us, be able to know that these are the alkali metals, alkaline earth, transitions, inner transitions, boron family, carbon family, nitrogen family, oxygen family. These are called the halogens or halogens, and these are the noble gases. Okay, this group is the S. Here's the P's over here. Helium is not a P. Helium belongs to S, but they slide it over here to make it look nice and neat, plus it acts like a noble gas. Here's the D's for daisy, and here's the S for fancy. Okay? All right. Check mark because we did that. Know the periodic law and how it relates to the arrangement of the periodic table. And so I'm going to write it down. This was last chapter, but we're going to repeat it again because we need to know it. So here's what it says. It says that when the elements are arranged in order, when the elements are arranged in order of increasing atomic number, there is a periodic repetition. Repetition or repeat, same thing, of their chemical, of the elements, oops, misspelled there, sorry, elements, chemical and physical properties. Okay, so that's the periodic law. You can pause it and look at it. I'm going to clear it and move on to number 9. Know the off-bow principle, Pauli's exclusion principle, and Hund's rule. Okay, so the off-bow principle says electrons enter orbitals. Electrons enter orbitals of lowest energy first. So if I have electrons on the 4th energy level, they can enter 4s, 4p, 4d, 4f, but they have to go into 4s first because it has the least amount of energy. After they fill up the s, they can go to the p. After they fill up the p, they can go to the d. After they fill up the d, they can go to the f. The Pauli principle says that no more than 2 electrons, no more than 2 electrons can occupy an orbital, can occupy an orbital. So think about when we draw, let's say 4s. We put an up and a down spin, and that's our 2 electrons. When we do the p's, we put an up in each of them first, And then we go back and put the downs, but notice we never put more than 2 in the orbitals. All right, Hund's rule says that 1 electron enters each orbital until all orbitals contain 1 electron. All orbitals contain 1 electron with a parallel spin. So let me clarify that. When I'm doing this over here, when I was filling my 4p, I know it can hold 6 electrons, but first I have to put 1 in each orbital. They all have parallel spins. That's Hund's rule. That's what he tells me to do. And then I can go back and start filling it with the others 3. Okay? All right, you can pause it if you need to. I'm going to clear it and move on. All right. It says to know the order in which energy increases for the s, p, d, and f orbitals. So s is always the lowest. P has a little bit more. D has more still, and F has the highest amount of energy. Valence electrons, know what they are and where they're located. Well, let's see if we can figure that out. And I think we can. There we go. Valence electrons are those located in the outermost energy levels. So I'm going to write this down. The valence electrons are the outermost outermost electrons in an atom. So if you go back to your periodic table, you need to know that this column has 1 valence electron. This one has 2. They're located in the S. This one has 3 because it has 2 in the S and 1 in the P. 4. The reason it's 4 is 2 are in the S and 2 are in the P. 5. 2 in the S, 3 in the P. 6. 2 in the S, 4 in the P. 7. 2 electrons in the S and 5 in the P. And then finally 8 here because 2 are in the S and the other 6 are in the P. This has 2 valence electrons because it only has 2 electrons. 1 valence electron here. You've got to know that. Know why some elements gain electrons and some elements lose electrons. Everybody is after the magical number 8 from the octet rule. Okay, so what we're trying to do is we're going to have some electrons, some electrons gain. Let me try that again. How about if I wrote some elements? Some elements gain electrons so they can obtain the noble gas configuration. So let me show you what I'm talking about there. If I'm sulfur, to get to this noble gas argon, I need to gain 2 electrons because that would give me 18, so that would be 1, 2 electrons, and I would be a lot like argon. If I were iodine, I need to pick up 1 more, so I could be like xenon. If I were nitrogen, I need to pick up 1, 2, 3 more, so I could be like neon. So from here over, they want to gain electrons. If you move on to the other elements, some elements will find it easier to lose electrons so that they can have the noble gas configuration. All right, so let's talk about those. Over here, sodium, lithium, hydrogen, not hydrogen, but lithium, sodium, potassium, rubidium, cesium, francium, they all have one extra electron. Well, if I get rid of that extra electron, it goes from 3 down to 2, so it now acts like helium. If I have sodium and I can get rid of that extra electron, it gives me 10, so I have that noble gas configuration of neon. If I'm potassium and I can lose 1 electron, then I have a noble gas configuration, or I have an electron configuration similar to argon. So that's their ultimate goal, because these are stable. Think about them, they don't want to react. All right, so I'm going to clear that and move on. Know the chemical importance of valence electrons. Valence electrons are the electrons that participate in bonding. The valence electrons are the electrons that participate in bonding. So they determine how reactive an element is going to be. All right, I'm going to stop there and go on to end this recording and then come back and do number 12.